Usually when we talk about, like, a medical diagnosis, there's this expectation of precision, like engineering, right? You break your arm, the x-ray shows that jagged white line, and the doctor just points at the film and says, there's the fracture.
Right, it's visible, it's tangible.
Exactly. But then you step into the world of neurodevelopment, and suddenly that x-ray machine is just useless. We look at a diagnostic landscape that is, well, entirely murky.
Yeah, it's a completely different paradigm.
It is, or to completely shift gears and, capture that exact same feeling of daunting, incomprehensible complexity, I want you to imagine something. Imagine you are tasked with designing a massive, bustling metropolis from absolute scratch.
Okay, building a city.
Right, but I'm talking about New York City, Tokyo, and London, all rolled into one massive, sprawling urban grid. You have to lay out every single highway, every alleyway, the residential zones, the high-voltage power lines, even like every single traffic light.
That is quite the urban planning job.
And here is the impossible catch, right? You have to place everything perfectly down to the absolute millimeter before a single drop of concrete is ever poured.
Because once that concrete sits...
You cannot change a thing.
Yeah.
Exactly. If you put a stoplight in the wrong place, the entire city gridlocks forever.
It becomes a completely binary outcome at that point. I mean, it either functions perfectly at 1 billion operations per second, or it's a useless multi-million-dollar paperweight.
Right.
And, we use analogies like city planning because we inherently crave visibility. We want to categorize these monumental engineering efforts in, like, human terms.
But in the physical reality we're exploring today, this metropolis isn't built on a continent. It's built on a piece of silicon the size of your fingernail.
Yeah, it's wild.
Welcome to the Deep Dive.
Yeah.
Today we are taking you on a monumental journey. We are going to explore the modern application-specific integrated circuit design flow, or as the semiconductor industry calls it, the ASIC design flow.
Which really represents the absolute boundary of engineering at the edge of physical reality.
It really does. So let's unpack the mission for today. Our goal is to understand exactly how an abstract idea in a system architect's head transforms into a physical silicon chip containing literally billions of microscopic transistors.
Billions, with a B.
Right. We're going to walk through the rigorous engineering flow, tracing the path from like behavioral code down to the atomic level. We'll look at the massive economics driving this space, and we're going to dive deep into the brutal physics challenges like electromigration that engineers have to solve to keep these microscopic cities from literally destroying themselves.
And to map out this journey, we're synthesizing an incredible stack of sources. We've got deep technical guides from Shinix Design breaking down the VLSI engineering flow. We're pulling from industry-level case studies on 5G infrastructure migration published by Microwaves and RF.
A lot of heavy reading for sure.
Oh, absolutely. We also have comprehensive engineering reports from Wevolver, and we're analyzing cutting-edge mitigation strategies for physical design failures from the NASCOM engineering community. Plus, test methodologies from Vidian and Mentor.
So a massive amount of data.
It is, yeah. But we're threading it all into a single cohesive narrative, from the very first written specification all the way down to the final silicon wafer.
Consider this your masterclass, We're going from the boardroom to the atomic level. And I think the most logical place to start, before we even talk about how these chips are made, is to ask the most fundamental question. Why are we making them in the first place?
Right, the motivation.
Because designing an ASIC is incredibly difficult. It's heavily constrained, and it's shockingly expensive. So what's the economic driver here?
Well, the answer usually comes down to a very specific tipping point in technology scaling. If we look at the telecom industry right now, specifically like the global rollout of 5G cellular infrastructure, we see this tipping point really clearly.
Okay, walk us through that.
According to the data from Microwaves and RF, 5G is not just a small incremental step up from 4G LTE. It's a massive physical leap that introduces brutal financial and energetic demands.
How brutal are we talking?
Well, to deliver the exact same geographical coverage as LTE, 5G requires 3 times as many base stations. It demands 3 times as much power per station, and it costs 4 times as much to deploy.
Wait, 3 times the base stations?
Yeah.
That comes down to the frequency spectrum 5G uses, right?
Yeah.
It relies heavily on millimeter wave frequencies.
Exactly.
And those high frequencies can carry massive, gigabit level payloads of data. But the physics of radio waves dictate that they just can't travel very far.
No, they degrade incredibly fast.
Furthermore, they get blocked by almost anything in the physical environment. Like even a person's hand holding a smartphone can severely attenuate a millimeter wave signal.
Yeah, that physical limitation forces a massive architectural shift for telecom companies. To compensate for the short range and the signal degradation, they have to build incredibly dense networks using massive MIMO, that's multiple input, multiple output antenna arrays.
Right.
You're no longer transmitting a broad umbrella-like signal. You're actively beamforming multiple streams of data to individual users simultaneously. Now, traditionally, when telecom companies built 3G or 4G infrastructure, they relied heavily on FPGAs to handle this digital signal processing.
Okay, let's ground that concept for a second. FPGAs, meaning field programmable gate arrays. An FPGA is essentially like a massive sea of generic, unassigned logic gates, right? It acts as a blank slate of hardware.
Exactly, yeah. You buy the chip completely off the shelf, and then your internal engineering team programs it to become whatever logical circuit you need it to be.
And the allure of an FPGA is just supreme flexibility, I imagine. Because telecom standards evolve. The 3GPP consortium might release a new specification, or, I don't know, your internal team might develop a radically more efficient algorithm for processing radio signals, like 6 months after you've bolted the base station to the cell tower.
Which happens all the time.
Right, so with an FPGA, you simply transmit an update over the air. The chip physically reconfigures its internal hardware routing to create new data paths, and boom, you instantly have an upgraded system without ever dispatching a technician to replace the physical silicon.
Yeah, that sounds like an absolute dream for infrastructure design, doesn't it?
It really does. So why on earth would the industry move away from something so adaptable?
It all comes down to what chip designers call the PPA triad. That stands for performance, power, and area. FPGAs give you unparalleled flexibility, but that adaptability carries a severe architectural penalty.
I found the empower.
Huge penalty. To make a chip reprogrammable in the field, the manufacturer has to build in a massive infrastructure of generic routing matrices and redundant logic blocks.
Oh, I see.
The vast majority of the transistors on an FPGA aren't actually computing your data. They're merely acting as programmable switches to route signals from one configurable block to another.
So you're carrying an immense amount of dead weight on the silicon.
A staggering amount. And that dead weight causes high static power consumption, often referred to as leakage, and it severely limits your maximum clock frequency because the signals have to travel through all those programmable switches.
It's like driving through a city where every single intersection has a toll booth.
Perfect analogy.
Yeah.
And in the 5G era, where you already need 3 times the power and 3 times the base stations just to maintain coverage, the power inefficiency of an FPGA suddenly spirals into a catastrophic financial burden for telecom operators.
So the electricity bill just eats them alive.
Literally. And this is where the ASIC re-enters the conversation.
Your application-specific integrated circuit. Hardwired, immutable logic.
Right. An ASIC is customized down to the individual transistor level to perform one specific mathematical or logical job and absolutely nothing else. There is no redundant logic. There are no generic routing matrices eating up power. It is pure, concentrated efficiency. To put the performance gap into perspective, the sources highlight that a custom ASIC built on an older, cheaper 22-nanometer or 28-nanometer planar process can actually match the logical throughput of a state-of-the-art 16-nanometer FinFET FPGA, and it does it while operating at a significantly lower power envelope.
That's incredible. But the economics of this transition are fascinating because designing an ASIC from a blank sheet of paper is notoriously expensive, isn't it?
Oh, extremely. Let's break down the financial math driving this industry. When you build an FPGA-based system, your upfront cost for the physical silicon design, what the industry calls non-recurring engineering, or NRE, is effectively zero.
Right, because AMD or Intel already spent the money designing it.
Exactly.
Yeah.
The manufacturer has already spent the billions of dollars required to design the chip and bring it to market. You just purchase it. However, because you're buying a massive, complex, reprogrammable die that is incredibly difficult to manufacture, the unit cost is astronomical.
How astronomical?
Well, an advanced FPGA designed for high-bandwidth communications, like the Manning's UltraScale Plus series, might cost anywhere from $30 to $50 per chip, even when you're purchasing in massive bulk volumes.
$30 to $50 per chip in bulk. That adds up fast.
And if you attempt to buy just 1 or 2 off a distributor shelf, you're looking at roughly $975 per chip.
$975 for a single piece of silicon. That is wild. Now contrast that with the ASIC development cycle.
Okay, so let's assume your telecom company decides to build a custom 16 nanometer FinFET ASIC for your new massive MIMO base stations. Your NRE, which encompasses, licensing, third-party intellectual property, paying a massive team of design and verification engineers for a year, and purchasing the incredibly expensive extreme ultraviolet lithography mask sets from the foundry that will run you approximately $18 million upfront.
Wait, 18 million. You are 8 figures in the hole before you even have a single physical chip in your hand to test.
It is a massive barrier to entry. But this is the magic of economies of scale. Because you only designed exactly the logic gates you absolutely need, the physical die size of your custom ASIC is incredibly small.
Right.
So a foundry like TSMC can print thousands of these tiny dies on a single 300 millimeter silicon wafer. Consequently, your manufacturing unit cost plummets to roughly $6.20 per chip.
Wow. Going from a $50 unit cost on an FPGA down to $6.20 for an ASIC. That's a fundamental shift in your business model. You face a massive upfront cliff, sure, but it's followed by a flat, expansive plane of cheap manufacturing.
And if we calculate the break-even point, assuming a conservative production run of 1 million units per year for a global 5G rollout at that volume, the initial $18 million investment for the custom 16-nanometer ASIC pays for itself in just 13 months when compared to procuring bulk FPGAs.
Just over a year. That's nothing in infrastructure terms.
Exactly. And after month 13, you're saving tens of millions of dollars annually on component costs alone. Furthermore, that equation doesn't even factor in the massive reduction in the ongoing electricity bill because, like we said, the ASIC consumes a fraction of the wattage.
But I have to challenge this model, though. We established that ASICs are entirely rigid. They are literally etched into stone or, well, silicon. What happens if the algorithms change? What happens if the global 3GPP standard updates a critical protocol?
Yeah, that's the risk.
Because FPGAs absorb those changes gracefully. If you bolt an ASIC into a cell tower and the standard evolves, you just have a multi-million-dollar brick.
And that is the exact dilemma that keeps ASIC architects awake at night. Nobody wants to deploy a multi-million-dollar brick. So modern hardware designers have developed brilliant methodologies to bake flexibility back into a hardwired chip without sacrificing the PPA benefits.
So creating a hybrid architecture.
Precisely. One prominent strategy is incorporating embedded standard processor cores directly into the physical ASIC layout. You drop in a hardened ARM Cortex core or perhaps an open source RASCV core.
Oh, interesting.
Because these cores are hardwired into the ASIC, they are incredibly dense and power efficient, but their primary function is to run software. Therefore, you can update the software firmware running on the ARM core to handle evolving control plane protocols while leaving the heavy, computational, intense data plane signal processing to the fixed, custom logic gates of the ASIC.
Ah. So you capture the raw, brute force speed of hardware for the heavy lifting and retain the flexibility of software for the overarching control logic.
Exactly. And an even more cutting-edge trend is the adoption of the eFPGA, an embedded FPGA.
Wait, putting an FPGA inside the ASIC?
Yep. Companies like Acronix and FlexLogix have created business models around licensing small blocks of reprogrammable FPGA fabric that you physically embed directly into your custom ASIC die.
It acts as an architectural get-out-of-jail-free card.
Exactly. You dedicate a small physical area to a few thousand reprogrammable logic elements. It's just enough capacity to tweak an algorithm or patch an unforeseen hardware bug post-deployment without compromising the massive efficiency gains of making the remaining, say, 95% of the chip a fixed ASIC.
It's like constructing that massive concrete metropolis we talked about, but deliberately leaving one central city block as an open part where you can set up temporary structures depending on what the city needs that specific year.
That's a great way to look at it. You optimize the vast majority of the design for pure performance and dedicate a tiny fraction of your silicon real estate to adaptability as an insurance policy.
Okay, so we've established the economic mandate. The $18 million upfront cost is easily justified at scale. This brings us to the core of this deep dive. How do you actually organize a team of engineers to build a microscopic metropolis containing billions of transistors without making a single fatal error?
Which is basically a miracle every time it happens.
Right, so this takes us to the very beginning of the flow, architecture and front-end logic, specifically defining the chip specification.
Everything begins with the specification document. Before anyone even touches a keyboard to write a single line of code, the system architects sit down to define the absolute limits of the mission.
The constraints.
Right. This is where the PPA triad performance, power, area is explicitly quantified. What is the target clock frequency? Are we aiming for 1 gigahertz or 3 gigahertz? What's the absolute maximum thermal dissipation the package can handle? What is the maximum allowable die size in square millimeters?
And crucially, this is where the architects select the technology node, correct? Deciding between utilizing a 7-nanometer FinFET process or an older, mature 28-nanometer planar process, which, as we saw with the economics, drastically alters that initial NRE calculation.
Choosing the fabrication node is perhaps the most massive strategic decision in the entire process. Moving to a smaller, more advanced node like 7-nanometer grants you incredibly high transistor density and superior dynamic power efficiency. But it introduces staggering design complexity, strict lithography layout rules, and drastically higher mass costs at the foundry. During this specification phase, the architects are also mapping out what third-party intellectual property or IP blocks they need to license.
Because nobody builds a metropolis completely from scratch. You don't invent a new molecular structure for a water pipe if you can just purchase the blueprint for an industry-standard pipe that is guaranteed not to leak.
Exactly. If your ASIC needs to communicate over a high-speed PCIe Gen 5 bus or interface with LPDDR5 memory modules, you absolutely do not waste thousands of engineering hours designing a memory controller from the ground up.
You just buy it.
You license a pre-verified, silicon-proven IP block from a specialized vendor like Synopsys or Cadence. The architects map out the integration of all these external blocks, define the internal memory maps, and plan the overarching clock domains and reset strategies.
So once this golden reference specification is locked in, the design moves into design entry and functional verification.
Right. Let's unpack the design entry phase. The engineers begin writing the chip, but they aren't using a graphical interface to draw little schematic symbols of transistors on a screen.
They're writing code using a hardware description language, or HDL. The dominant languages in the semiconductor industry are System Verilog and VHDL.
Yes.
To clarify this, for those of you who might write software in Python or C++I, writing in an HDL requires a fundamentally different mental model, doesn't it? Because software executes sequentially. The CPU reads one line, executes it, and moves to the next. Hardware, by definition, happens all at once.
And that distinction is the absolute highest hurdle for software engineers transitioning to hardware. In an HDL, you are not writing a sequential list of instructions. You are describing the continuous flow of data between physical registers, entirely governed by the rhythm of a clock signal.
It's all happening concurrently.
It is a fully synchronous environment. You're describing concurrent physical behavior. You might write a block of System Verilog that describes the behavior of a multiplexer, which is a logic gate that selects between multiple inputs, and another block that describes a flip-flop, which is a tiny 1-bit memory element.
And they run at the same time.
In the physical silicon, those two distinct structures will be evaluating their inputs and operating simultaneously on every single rising edge of the clock.
Okay, so the design team is solely focused on coding the intended behavior of the chip. What is the verification team doing concurrently? Because the sources repeatedly emphasize that verification, not design, is actually the most massive bottleneck in the entire development cycle.
Oh, yeah. Verification consumes an enormous percentage of the project timeline and compute resources. Because a single, minute logical bug that makes it into the final silicon can force a complete respin, costing millions of dollars and months of time.
You can't just push a software patch to fix a broken wire.
You cannot. So the verification team utilizes robust frameworks like UVM, the Universal Verification Methodology, to construct incredibly elaborate simulated environments. They essentially build a virtual test bed designed to bombard the RTL code, the register transfer level code the designers just wrote, with every conceivable randomized combination of inputs to force it into corner cases and just watch it break.
It's akin to stress testing the digital blueprints of our city by simulating a hurricane, a localized earthquake, and a massive traffic surge, all at the exact same moment, just to see if the structural integrity of the bridges holds up.
That is exactly what they do. And they embed SVA System Verilog assertions directly into the RTL source code. Think of assertions as immutable laws of physics for the chip.
Give me an example of an assertion.
An assertion explicitly states something like, under no circumstances, in any possible state-machine transition, should this specific error flag ever be asserted high while the data valid signal is low. If the random simulation ever creates a condition that violates that rule, the test environment immediately halts and flags the failure for the designers.
The sources also detail formal verification, which seems to take this concept to a much more rigorous level.
Formal verification is a fascinating departure from traditional simulation, because instead of running billions of simulated clock cycles with pseudo-random inputs and merely hoping your randomized test hits the hidden bug, formal verification employs advanced discrete mathematics.
Oh.
The formal tool treats the HDL code as a massive set of Boolean mathematical equations and attempts to mathematically prove that the design can never violate its assertions under any possible sequence of events.
That proves it mathematically.
It doesn't guess, right? It performs an exhaustive mathematical analysis of the entire state space of the design.
So once the code is written, simulated exhaustively, and mathematically proven to be bug-free, we reach a critical transition. The blueprints are perfect, but they are still just abstract behavioral concepts on a monitor. We need to turn behavior into physical structure. That brings us to RTL synthesis.
And synthesis is the bridge between the abstract software domain and the physical hardware domain. You take your behavioral system Verilog code and you feed it into a massive synthesis compiler tool, such as Synopsys Design Compiler.
Okay.
Alongside your code, you provide the tool with a technology library. This library contains the actual physical standard cells provided by the specific Silicon Foundry-like TSMC or Samsung that will actually be manufacturing the chip.
Standard cells being the fundamental building blocks of the ASIC, the raw logic gates like A and D gates, OR gates, inverters.
Exactly. The synthesis tool reads your behavioral description, mathematically analyzes the logic required to achieve that behavior, and translates it into a massive, interconnected map constructed entirely out of those physical standard cells. This structural map is known as a gate-level netlist.
A helpful way to visualize synthesis is taking a recipe for a cake, which represents the RTL code describing how the cake should taste and rise,
Yep.
and using a supercomputer to calculate the exact molecular composition of every single atom of flour, sugar, and butter required to physically manifest it.
I love that.
You end up with a netlist that specifies you need 4 million physical A and D gates,
Well-
2 million OR gates, and here is the exact topological wiring diagram connecting them.
And the synthesis compiler does much more than a simple translation. It actively optimizes the netlist to meet the constraints you define back in step 1. It tries to map the logic in a way that satisfies your timing, area, and power budgets.
Right.
A great example highlighted in our sources involves modern mobile and AI chips. Engineering teams will deliberately command the synthesis tool to target a 35 to 50% multi-bit flip-flop ratio.
Let's break down the multi-bit flip-flop, because a standard flip-flop stores a single bit of data, right? A
Yeah.
1 or a 0. Why would a designer want to merge them together?
Consider the physical reality of a flip-flop. Every single sequential element in the chip must be physically connected to the clock signal. That requires routing microscopic metal wiring to the cell, and the cell itself requires a tiny internal inverter to drive the clock signal into the latching mechanism. If you instantiate millions of individual single-bit flip-flops, you are duplicating that internal clock inverter and the local clock wiring millions of times. That redundancy consumes a massive amount of dynamic power every single time the clock ticks.
Which is billions of times a second.
Right. By utilizing multi-bit flip-flops, say physically combining 2, 4, or even 8 flip-flops into a single larger standard cell, those internal bits can share a single robust clock inverter and share the same localized clock routing. This architectural choice drastically reduces the overall dynamic power consumption of the chip's clock network.
It's like having 4 adjacent houses agree to share a single wide driveway instead of paving 4 separate narrow driveways. It dramatically reduces the total amount of concrete required.
That's spot on.
Once the synthesis tool handles all of this complex mapping and optimization, we have to deal with the sheer scale of the output.
Yeah, because a modern gate-level netlist might contain billions of logic gates. It is simply too massive for the downstream physical layout tools to ingest and process all at once.
So they have to break it up.
The engineering team must perform chip partitioning. They break this monolithic netlist down into smaller, layout-friendly functional blocks or subsystems. They then model and verify these individual partitions using high-level languages like C++ or System C to ensure the overarching data flow and communication protocols between these major subsystems remain intact.
So we have partitioned the city into manageable municipal districts. But before we actually start laying down the physical roads and buildings, we have to implement Designed for Test, or DFT.
Ah,
The
yes.
sources make it abundantly clear that DFT is an absolute non-negotiable requirement. Why is that?
Because the physical manufacturing of silicon is a fundamentally imperfect, brutal process. We are attempting to print structures that are only a few dozen atoms wide, using extreme ultraviolet light that is generated by blasting microscopic droplets of tin with a high-power laser.
Which is just science fiction.
It really is. But because it's so extreme, a single stray particle of dust in the clean room, a minute statistical variation in the lithography chemical resist, or a microscopic defect in the silicon crystal lattice itself can break a wire or short a transistor.
So even if the mathematics and formal verification proved our logic was 100% perfect, the physical reality of the fabrication plant can still produce a broken chip.
Exactly. You could design an architecturally flawless ASIC, manufacture a batch of 1 million units, and discover that 5% of them are physically dead on arrival due to manufacturing defects. If you solder those defective chips into a 5G base station or an autonomous vehicle, you have a catastrophic hardware failure on your hands.
Which you cannot afford.
DFT is the engineering science of finding those physical manufacturing defects before the chip ever leaves the factory floor.
The scale of the problem seems insurmountable, though. How do you thoroughly test a chip containing billions of transistors? You can't just plug it into a motherboard and run a benchmark test, right? It would take centuries of continuous operation to manually trigger every possible logic path.
It would. Therefore, engineers must deliberately insert dedicated, specialized test logic directly into the synthesized netlist specifically for this purpose.
Okay, how does that work?
The foundational technique across the industry is called scan chains. Remember the flip-flops storing the data states. During the DFT insertion phase, the EDA tools meticulously replace the standard flip-flops with special scan flip-flops. These scan variants feature an extra multiplexer on their input that allows them to be logically stitched together into one massive continuous chain.
Like stringing thousands of Christmas lights together into one long strand.
Exactly. When the newly manufactured chip is placed onto an automated test equipment machine on the factory floor, it is put into a dedicated test mode. This long chain of flip-flops suddenly acts like a giant shift register.
Yeah.
The massive tester machine pumps a highly specific, calculated sequence of ones and zeros, a test pattern, directly through this chain, serially loading a specific starting data state into every single flip-flop in the chip simultaneously.
Wait, so you bypass the normal operational logic of the chip entirely and just force-feed every sequential element a predetermined starting state?
You got it. Then, you flip the chip back into its normal functional mode, but only for exactly one single clock cycle. The millions of combinational logic gates process that forced starting state and capture the resulting output back into the flip-flops. Finally, you revert the chip back to test mode and shift all of those captured results back out to the external tester machine.
And the automated tester knows exactly what that final sequence of ones and zeros should look like if the physical silicon is structurally perfect.
Yes.
If a 1 emerges from the scan chain when it mathematically should have been a 0, with certainty that a microscopic metal wire is physically broken somewhere in the specific logic path that fed that flip-flop.
Exactly. And the complex process of generating those specific sequences of ones and zeros is called ATPG automated test pattern generation. ATPG software tools mathematically analyze the netlist to calculate the absolute minimum set of test patterns needed to expose specific physical defect models.
Like what kind of defects?
Well, they target stuck-at faults, where a wire is physically shorted to the power rail or ground and stuck at a permanent 1 or 0. They also target transition faults, which are more insidious. This is where a wire might be slightly too thin due to a lithography error, increasing its resistance so the signal moves too slowly to meet the required clock cycle time.
Okay, that covers the combinational logic. But modern ASICs are dominated by vast arrays of memory, like SRAM caches. You can't string millions of memory cells into a scan chain, right?
Yeah.
The routing overhead would be astronomical.
Right. For embedded memory, the industry relies on MBS memory built-in self-test. The DFT engineers insert tiny, dedicated logic controllers into the netlist, placing them directly adjacent to the large memory blocks.
What do those controllers do?
When you power up the chip in the factory, these MBS controllers automatically wake up. They generate and write complex mathematical algorithms of data into the memory arrays, read the data back out, and perform high-speed comparisons to detect any physical defects in the memory cells or the address decoders.
So the chip is literally endowed with the logic to interrogate and test itself.
It goes a step further, actually. Because memory arrays are so incredibly dense, they take up a massive amount of physical area on the die, making them highly susceptible to random manufacturing defects. To combat yield loss, designers build extra redundant rows and columns of memory cells into the physical array.
Oh, I see where this is going.
If the MBIST controller detects a defective cell during its self-test routine, it can dynamically reroute the internal addressing logic to permanently bypass the broken cell and swap in a spare redundant cell instead.
The chip physically repairs its own manufacturing defects on the fly. That is unbelievable.
It's essential for yield.
Our sources from Vidian provided a highly detailed case study on this DFT implementation. They outlined a hierarchical DFT flow for a quad-core ARM Cortex A75 subsystem. The metrics they achieved highlight the immense scale of this challenge.
Yeah, the data points from that A75 subsystem are revealing. Simply to test for all the static stuck-at faults within that specific block, the ATPG tool had to generate 17,280 distinct test patterns. Wow. Feeding tens of thousands of patterns into a chip sequentially, utilizing an external tester machine that costs millions of dollars to operate, consumes incredibly expensive factory floor time.
So how do they mitigate the tester time if they can't reduce the number of patterns required to guarantee coverage?
They implement a sophisticated technique known as embedded deterministic test, or EDT compression. It uses on-chip decompressor logic, often built using XOR trees.
Okay.
The external tester sends in a highly compressed seed of data, and the internal EDT logic expands that seed into the massive pseudo-random test pattern required by the scan chains. The results are captured, compressed back down by an internal compactor, and sent back to the tester.
That saves a ton of time.
It really does. By combining EDT compression with on-chip clock controllers, the engineering team in the Vidian case study achieved over 99% fault coverage.
Meaning they could statistically guarantee that if 99% of the modeled manufacturing defects existed anywhere in the silicon, this specific suite of tests would detect them.
Exactly, and they achieved this while keeping the tester cycle times economically viable.
Achieving over 99% fault coverage gives the manufacturer incredible confidence that the silicon shipping to the customer is functionally sound.
Yes, it does.
So the front-end phase is now complete. We have the architecture defined, the behavioral code verified, the structural gate-level netlist synthesized, and the test logic injected. The logical blueprint is mathematically perfect. But, however, it remains a list of logic gates and abstract connections. We now transition into the back-end physical design phase. We have to actually map this logic onto physical silicon real estate. And this begins with floor planning.
Right. Floor planning is the critical act of defining the physical macro structure of the die. We establish the exact physical boundaries of the chip in millimeters. We strategically place the I/O pads, the physical input and output pins that will eventually bond to the package and connect the chip to the printed circuit board. And crucially, we place the hard macros.
Hard macros represent the large, pre-designed fixed blocks of physical layout, correct?
Yeah.
Like the massive SRAM memory arrays or the analog IP blocks like the PCIe physical layer we licensed earlier.
Exactly. Returning to your metropolis analogy, defining the die size establishes the absolute city limits. The I/O pads act as the shipping ports and interstate highways leading out of town. The hard macros are the massive, immovable industrial zones or sports stadiums.
You got to build around them.
The physical designer must place these massive, dense structures first, because the remaining millions of tiny standard logic cells have to be organically distributed around them. The placement of these macros must be highly strategic, aiming to minimize the physical distance data must travel between critical subsystems to reduce latency.
But the absolute most critical infrastructure built during floor planning isn't just where you place the logic, right? It is how you deliver electricity to the entire city. Power planning and the design of the PDN, the power distribution network.
The PDN is arguably the single most vital physics-bound infrastructure on the chip. Your objective is to deliver power VDD and VSS, the positive supply, and the ground return from the external pins to literally billions of transistors scattered across the entire silicon die.
And you must accomplish this without the voltage dropping significantly.
That's the hard part. If a given transistor requires 0.8 volts to switch states at the required speed, and it only receives 0.7 volts because the power grid above it is too resistive, that transistor switches slower, the timing path fails, and the entire system crashes.
So you have to engineer an incredibly robust, low-resistance electrical grid covering the entire chip.
Yes. You construct a massive intersecting grid of vertical and horizontal power straps utilizing the thickest, lowest resistance metal layers available at the very top of the layer stack. This is not driven by intuition. It is governed by rigorous electrical physics. The source provided the exact foundational equation physical engineers use to determine the geometry of this grid.
Yeah, I am looking at the equation right here. W equals IP divided by RJ. Let's translate this math into physical reality.
Okay, so W represents the minimum ring width, calculating exactly how wide the physical metal power trace needs to be drawn. It represents the peak supply current, the absolute maximum amount of current the integrated circuit will draw when all logic blocks are firing simultaneously.
And RJ.
Finally, RJ represents the current carrying capability of the specific metal layer you are routing on. That's a metric provided by the foundry based on the metal's sheet resistance and thickness.
So it's a straightforward ratio. If the peak current demand of the chip goes up, you mathematically require wider metal traces to carry it safely. If the physical capability of the chosen metal layer is weak, you must widen the trace to compensate.
Exactly.
It's fluid dynamics. If you need to push a massive volume of water at high pressure through a city block, you need a wider primary pipe. Otherwise, the friction causes a pressure drop, or worse, the pipe bursts.
And if a pipe bursts inside an ASIC, it manifests as a localized extreme voltage drop that stalls the logic, or, over time, the massive current density literally melts and migrates the metal wire. We'll dive deep into that melting phenomenon electromigration shortly, but for now, the floor plan is locked in, the macroscopic power grid is laid down, the macro blocks are placed. This allows the tools to proceed to placement.
Okay, placement. This is the stage where we finally drop all the standard cells, the millions of microscopic A&D gates or gates and flip-flops that constitute the actual synthesized logic into the remaining empty space on the die.
Right. The placement algorithms arrange these standard cells into strictly defined horizontal standard cell rows across the core area of the chip. The automated EDA tool executes this in several distinct algorithmic stages.
Walk us through them.
First is global placement, where the tool mathematically calculates the optimal rough location for every cell based entirely on its logical connectivity to other cells, trying to minimize the total length of wire required to connect them. Then comes legalization, where the tool physically snaps the cells into the actual legal grid rows, ensuring none of their physical bounding boxes overlap.
Because they can't physically sit on top of each other.
Right. Finally, detailed placement performs micro-optimizations, swapping adjacent cells or flipping their orientation to fine-tune the routing tracks and optimize the signal timing.
Here is the conceptual hurdle I struggle with, though. When dealing with hundreds of millions of individual logic gates, how does an automated tool decide where to put everything without inadvertently creating an unsolvable physical traffic jam?
What do you mean?
Well, if you cluster too many highly interconnected logic gates into one small physical quadrant, there simply won't be enough physical area available on the metal layers above to route all the microscopic wires needed to connect them.
What you're describing is known in the industry as routing congestion, and it is the absolute bane of a physical layout designer's existence. If a localized region becomes too congested during placement, the detailed routing tool, which runs much later in the flow, will literally fail to find a physical path for every wire. It will leave opens, and the design cannot be manufactured.
So how do you predict and solve a traffic jam before you've even built the roads?
Historically, it required intense manual intervention. But modern EDA tools employ sophisticated congestion-driven placement algorithms. And what is truly revolutionary, however, is the integration of machine learning into this stage.
Oh, ML is stepping in.
The AI analyzes the logical graph connectivity of the netlist and evaluates the early, unrefined placement configurations. It uses trained models to accurately predict where dense routing bottlenecks and localized thermal hotspots will occur before the computationally heavy, detailed routing even attempts to connect them.
It generates a predictive model of the future layout.
It produces a localized heat map of routing probability. If the ML model flags a specific tiny quadrant and says, based on the connectivity graph, this area has a 95% probability of being unroutable if you leave these cells here, the placement engine dynamically reacts.
It changes the plan.
Exactly. It preemptively spreads those specific cells apart, deliberately lowering the placement density in that quadrant to reserve more physical space for the impending rush of metal wires. It's predictive, algorithmic urban planning.
That is remarkable. So the standard cells are now placed. The structural foundation of the city is set. But an ASIC isn't just a static arrangement of structures. It is a highly dynamic, highly synchronized state machine.
Very dynamic.
Every single flip-flop in the massive design needs to know exactly when to shift its data. This brings us to the heartbeat of the chip. Clock tree synthesis, or CTS.
Yes, the clock signal is the heartbeat. Every sequential element on the die, every single flip-flop must operate in perfect synchronization. Achieving this is a monumental physical challenge governed by the speed of light and electrical resistance.
Let's explore why this is so difficult. Because conceptually, a clock is just a simple electrical signal that oscillates between high and low, a 1 and a 0, billions of times a second.
Okay, imagine an orchestra consisting of 1 billion musicians spread out over a massive, sprawling stadium.
Okay, a big stadium.
The conductor stands at the very center, waving the baton. The musicians physically closest to the conductor see the baton move and play their note immediately. But the musicians seated at the very back of the stadium see the baton a fraction of a second later because light, despite being fast, still takes time to travel that immense distance.
Yeah.
If they play their note exactly when they see the baton, the orchestra is hopelessly out of sync. It degrades into noise.
Wow, that makes sense. So in a silicon chip, the conductor's baton is the electrical clock signal originating from a central phase-locked loop, or PLL.
Yes.
The musicians are the millions of flip-flops scattered across the die. And the physical distance the electrical signal has to travel through the microscopic metal wires creates a measurable time delay.
Exactly. The time difference between the clock signal arriving at one flip-flop versus another flip-flop located somewhere else is called clock skew. If the clock skew becomes too large, one flip-flop might capture new data before the previous flip-flop in the logic chain was ready to send it. The sequence breaks, and the chip fails instantly.
So clock tree synthesis is the highly complex process of building a physical, hierarchical distribution network, a literal tree of metal wires and repeater buffers, designed to ensure the clock signal arrives at every single flip-flop at the exact same picosecond.
Yes. And physical designers employ several different topological strategies for constructing this distribution network, each carrying intense trade-offs. The sources from Genix and VLC Guru analyze 4 primary topologies. Let's examine the first, the symmetrical H-tree.
The H-tree. This implies it branches out physically resembling the letter H over and over again.
Precisely. The main clock signal starts in the dead center of the die, splits equally left and right, then splits equally up and down at the ends of those branches, forming a massive H. It repeats this fractal splitting pattern at the end of every branch until it covers the die.
Okay.
Because the physical geometry is perfectly symmetrical, the electrical path length and resistance to every single endpoint are theoretically identical. This provides exceptionally good skew control. However, it consumes a massive amount of premium routing resources because you are forcing the metal wires into this rigid geometric pattern regardless of where the actual flip-flops were placed by the placement tool.
It's an inflexible grid.
Yeah.
What is the second topology?
The clock mesh. Instead of a fractal tree branching out, you construct a massive, dense grid of intersecting thick metal wires, a literal mesh blanketing the entire core area of the chip, and you drive the clock signal into it simultaneously from multiple buffered points. The underlying flip-flops simply route up and tap into the mesh wherever they happen to be located.
A blanket of timing. That seems robust and field-proof against localized variations.
It is exceptionally robust for time enclosure. It offers the absolute best tolerance against process variations and gives you incredible near-zero skew control. But consider the electrical trade-offs.
The capacitance, right. If you have to electrically charge and discharge an entire massive grid of metal covering the entire chip from 0 volts to 1 volt billions of times every single second, that requires a staggering amount of dynamic current.
The dynamic power consumption of a full clock mesh is exorbitant. In power-sensitive, battery-operated designs like mobile phone, SOCs, or IoT devices, implementing a full clock mesh is typically a complete non-starter. It would drain the battery in minutes.
So the H-tree is heavy on routing resources, and the mesh is an absolute power hog. What is the third option?
The spine or fishbone structure. You route a thick main vertical trunk of clock signal straight down the center of the die, the spine. Then you branch off smaller horizontal ribs, the fishbones that run across the cell rows and connect to the flip-flops.
Makes sense.
It is very simple for the automated tools to route, it has very low latency, and it consumes very low dynamic power. However, because the electrical paths are not perfectly symmetrical, it suffers from moderate clock skew. The designer is intentionally sacrificing precision to save power and simplify routing.
And the fourth topology is the hybrid, which attempts to strike a balance, right?
Right, a hybrid mesh tree architecture. You utilize a sparse tree structure to distribute the clock signal globally across the large distances of the chip to save power, but you drop down into small, localized, dense meshes in highly critical areas to guarantee precision exactly where you need it most. It attempts to balance the extreme variation tolerance of a mesh with the lower power profile of a tree.
So all of these traditional physical topologies are fundamentally chasing the concept of zero skew. They are striving to ensure the clock edge arrives at every flip-flop simultaneously. But our sources highlight a massive paradigm shift in modern CTS logic called logical chain-based clock implementation. And it completely flips the pursuit of zero skew on its head.
It is one of the most elegant conceptual advancements in physical design. For decades, the gold standard was absolute zero skew, balance everything perfectly. But modern EDA algorithms realize that not every flip-flop actually needs the clock signal at the exact same picosecond. The tools now analyze the logical relationships, the data paths, between the flip-flops.
Walk us through how a flip-flop could not need the clock at the same time as its neighbor.
Okay, let's trace the signal. Flip-flop A launches data, and that data must travel to flip-flop B. However, between A and B, the data must pass through a highly complex, deep series of combinational logic gates, say, a massive multiplier circuit.
Okay, a long path.
Because that logic path is so long and dense, the electrical data signal takes a significant amount of time to arrive at the input of flip-flop B. If flip-flop B receives the clock signal at the exact same time as flip-flop A, the data simply won't have arrived yet. Flip-flop B will capture old data. This is called failing the setup time requirement.
Gotcha. And in the old paradigm of zero skew, to fix that setup violation, you'd have to physically intervene. You'd have to rip up those logic gates, swap them out for larger, faster, power-hungry transistors to force the data signal to propagate faster through the multiplier.
Exactly. But with logical chain-based optimization, the synthesis tool employs the concept of useful skew. Instead of forcing the data to move faster, the tool intentionally delays the clock signal traveling to flip-flop B.
Oh,
Right.
you intentionally command the conductor to wait an extra microsecond before pointing the baton at the second musician.
Exactly. You intentionally introduce physical clock skew to shift timing slack from one logical stage to the next. By purposefully delaying the clock edge arriving at flip-flop B, you grant the slow data signal more time to arrive and stabilize, fixing the setup violation dynamically.
That is brilliant.
And you achieve this without having to upsize the logic gates, meaning you save power and routing space. You are solving a physical timing bottleneck by mathematically manipulating time itself rather than manipulating the logic structures.
That is incredibly elegant engineering. You stop fighting the clock skew and start using it as a surgical tool. The heartbeat is established, utilizing useful skew to keep the data flowing. The logic cells are placed. We now arrive at what is arguably the most terrifying and physically demanding phase of this entire process.
Oh yeah, here we go.
Constructing the nervous system,
Yeah.
connecting the millions of disparate components together at a microscopic scale. This is signal routing and the physics of failure.
Routing is where the abstract concept of a circuit collides violently with physical reality. The automated tools must now draw physical metal wires to connect all the standard cells and the clock trees, utilizing anywhere from 6 to 15 different stacked metal layers on the die.
Wow.
The process executes in two phases. First, global routing, which plans the general highway paths to avoid the congestion heat maps we generated earlier. And then detailed routing, which actually draws the exact geometric metal traces and drops the tiny vertical metal shafts that connect one layer to another.
And this is where the physics become terrifying. Because we are not merely drawing colored lines on a CAD screen. We are attempting to force electrical current through copper wires that are, in some advanced nodes, only a few dozen atoms wide.
Just unimaginably small.
That scale introduces brutal physics problems. Let's delve into the most destructive one highlighted in the NASCOM engineering source. Electromigration, or EM. What exactly is electromigration?
Electromigration is a physical phenomenon that will literally destroy an integrated circuit from the inside out over a period of months or years.
Seriously.
Seriously, when you force a very high current density through a microscopic metal interconnect, the electrons are moving with incredible kinetic velocity. As they flow, they constantly collide with the stationary metal ions that constitute the wire's physical crystal lattice structure.
I see. Think of a raging high-pressure river flowing through a narrow rock canyon. The water representing the electrons is moving with such extreme force that it actually begins to erode the rock walls, the metal atoms carrying them downstream.
That is the exact physical mechanism at play. Physicists refer to it as electron wind. The immense current density transfers momentum from the moving electrons to the stationary metal ions, physically dislodging them from the lattice and sweeping them along in the direction of the electron flow.
The physical metal wire itself is migrating across the chip.
Over time, the metal atoms are swept away from their original position. In the areas where the atoms are depleted, a microscopic void forms inside the wire.
Like a pothole.
Yeah, and this void increases the local electrical resistance, which generates more heat, which accelerates the process until the connection is entirely severed. Conversely, in the downstream areas where those swept atoms accumulate, they form what are called hillocks, little jagged deposits of solid metal that grow outward, eventually bursting through the dielectric insulation and short-circuiting to an adjacent wire.
So voids sever the connection and hillocks short the connection. The chip slowly rips its own nervous system apart. And there is a foundational physics equation that calculates exactly how long a specific wire will survive before this catastrophic failure occurs. Black's equation.
Black's equation is the mathematical bedrock for calculating the mean time to failure, or MTTF, of a metal wire subjected to electromigration. The equation states that MTTF equals a constant A divided by the current density J raised to the power of N, all multiplied by the exponential function of E over KT.
Let's translate those variables into tangible concepts for the listener.
Okay, A is a structural constant based on the cross-sectional area of the wire. A thicker, wider wire inherently lasts longer. J is the current density, how much current is squeezing through that cross-section.
Right.
This is the killer variable, because J is raised to the power of N, which is typically an empirical factor around 2. A small increase in current density exponentially, not linearly, decreases the lifespan of the wire.
If you double the water pressure in that narrow canyon, the rate of erosion doesn't just double, it quadruples.
Exactly. The other vital component of Black's equation is the exponential term. Ia is the activation energy required to dislodge an atom, and KT represents Boltzmann's constant multiplied by the absolute temperature of the chip.
Temperature.
As the temperature of the silicon die increases, the metal crystal lattice vibrates more violently, fundamentally lowering the barrier of activation energy. It makes it significantly easier for the electron wind to dislodge the metal ions. Therefore, combining high localized current density with a high thermal footprint will exponentially accelerate electromigration and kill the ASIC prematurely.
So if I am a physical layout engineer and my analysis software flags a critical timing wire that is mathematically destined to melt in 6 months due to EM, what are my mitigations?
Well, the NASCOM source lists several highly effective physical design interventions. The most direct fix is downsizing the driver. If a specific logic cell is pumping too much aggressive current into a fragile wire, you swap that cell out for a smaller variant with lower drive strength, thereby lowering the current density J.
But wait, everything's a trade-off. If you downsize the driver cell, it pushes less current, meaning the signal travels slower to charge the capacitance of the wire.
Blah.
You might solve the electromigration, but you've just broken your timing constraints.
Exactly right. If timing constraints prohibit you from downsizing the driver, you must attack the wire itself. You can utilize layer hopping. You command the routing tool to bring the wire up to a higher, thicker metal layer in the stack. The upper metal layers on an ASIC are physically manufactured with a larger cross-sectional area, which naturally lowers the current density and makes them far more resistant to the electron wind.
What happens if the upper layers are completely congested with power routing, though?
Then you can apply non-default routing, or NDR rules. You instruct the router to ignore the standard minimum width design rules for that specific wire and draw it 2 or 3 times as wide on the same layer.
Got it.
Alternatively, you can use fan-out splitting. If one massive driver cell is pushing heavy current to 8 different flip-flops simultaneously, you clone the driver. You place 2 identical drivers in parallel, each responsible for driving only 4 flip-flops, effectively splitting the current load and the current density in half.
So you are systematically relieving the electrical pressure in the pipes.
Right.
But what about the vias? The microscopic vertical shafts connecting the different horizontal layers. The literature suggests they are highly susceptible to EM because all the current gets bottlenecked, funneling up the tiny vertical hole.
Vias are absolutely critical failure points. To mitigate this, engineers employ multi-cut vias. Instead of drilling one vertical shaft, you drop 2, 3, or 4 shafts in parallel. It splits the current flow and drastically lowers the localized resistance.
That makes sense.
And at highly advanced process nodes like 7 nanometer or 5 nanometer, the physical wire resistance skyrockets so exponentially that standard multi-cut vias are insufficient. The industry had to develop via pillars.
Via pillars, what makes them different?
Think of a via pillar as a massive structural column spanning multiple floors of a building. Instead of just hopping up one layer at a time with a tiny via pillar uses parallel, stacked segments of metal wire stitched together with dense arrays of vias across several intermediate layers to create a massive low-resistance vertical superhighway.
Oh, wow.
The NASCOM data reveals that by utilizing a via pillar to bypass the highly resistive lower layers and jump directly to a thicker upper layer, the effective metal resistance can drop from an astounding 55x down to 13x.
Dropping resistance from 55x to 13x is a massive physical optimization. It saves dynamic power, dramatically improves the signal timing, and completely neutralizes the threat of electromigration.
It's huge.
That addresses the long-term, slow-motion physical destruction of the wire. But there is another brutal physics problem that causes instantaneous failure. IR drop or voltage drop.
Right, IR drop is the loss of voltage potential as current flows through the inherent resistance of the metal power grid we built earlier. There are two categories, static and dynamic.
Static IR drop is just the application of standard Ohm's law, right?
Yep.
C equals I times R. The average current multiplied by the resistance of the metal strap. The longer the power strap stretches across the die, the lower the voltage gets by the time it reaches the transistor.
Yep, and that is easily modeled and fixed by widening the straps. Dynamic IR drop, however, is the true nightmare scenario for engineers.
Why is that?
Dynamic IR drop is caused by the sudden, highly synchronized switching activity of millions of standard cells simultaneously. When that carefully synthesized clock ticks and 2 million flip-flops switch state at the exact same nanosecond, they demand a massive, instantaneous gulp of electrical current from the power grid.
And the power grid, bounded by physics, cannot deliver it fast enough.
Exactly. The governing physical equation here is V equals L multiplied by DIT. L is the parasitic inductance of the power grid itself, and DIT represents the rate of change of the current over time. Because the switching event is incredibly fast, DT is an almost infinitesimally tiny fraction of a nanosecond, the resulting voltage drop is massive. The voltage at that specific localized spot on the die plunges violently for a fraction of a nanosecond. If the voltage drops below the threshold required by the transistors, the logic gates switch too slowly, the data arrives late, and the chip fails its timing constraints.
It's equivalent to turning on every single faucet and flushing every single toilet in a massive high-rise apartment building at the exact same millisecond. The water pressure in the local pipes drops to zero instantly. How do we engineer a solution to dynamic IR drop?
We implement decoupling capacitors, commonly referred to as decaps. During the placement phase, engineers strategically sprinkle these tiny decap standard cells all over the chip, specifically targeting areas near power-hungry logic blocks. A decap acts exactly like a localized water tower.
It stores a tiny, localized reservoir of electrical charge right next to the transistors.
Right. So when the clock ticks and the flip-flops demand that massive, instantaneous gulp of current, they don't have to pull it all the way from the distant main power grid, fighting the inductance.
Yeah.
They simply drain the local decap reservoir.
Oh.
The decaps provide that instantaneous surge of current locally, keeping the regional voltage absolutely stable during the switching event. Then, during the quiet portion of the clock cycle, the decaps slowly recharge from the main grid.
Are there other interventions?
Yes, other physical interventions include cell spreading, literally forcing the placement algorithm to artificially spread highly active, high-toggling cells further apart physically so they aren't all drawing transient power from the exact same localized spot. And cell padding, which creates artificial empty keep-out zones around a high-power cell to prevent other cells from crowding its local power supply.
It sounds as if the engineers are engaged in a constant, desperate battle against the fundamental laws of physics.
They are.
As transistors continue to shrink, the interconnect wires get thinner, the resistance skyrockets, electromigration worsens, and dynamic IR drop becomes exponentially more severe. But we have successfully routed the wires and mitigated the physical failures. We now enter the critical final phase, sign-off and tape-out.
The home stretch.
This is the ultimate exam before the blueprints are committed to silicon. The most rigorous component of this is STA static timing analysis.
STA is the definitive mathematical proof that the finalized physical chip will meet its target clock frequency. The EDA tool verifies every single timing path in the multi-billion gate design to ensure it meets stake. Set up time verifying the data arrives fast enough before the next clock edge, and hold time verifying the data remains stable long enough after the clock edge to be safely captured.
And the sources document a massive methodological shift in how STA is performed at advanced nodes, moving from pessimistic margins to POCV parametric on-chip variation. Walk us through the mechanism of POCV.
Well, in older, larger technology nodes, engineers utilized pessimistic, fixed safety margins. They would assume that the absolute worst-case scenario for manufacturing variation, such as slightly thicker oxide or slightly wider gate length, would simultaneously afflict every single transistor on a critical timing path.
Like planning for the worst.
Right. But at 7 nanometer and below, the variations are so pronounced that if you assume the worst-case penalty for every gate, the timing analysis fails completely. The mathematical model suggests the chip won't work, forcing you to over-design the chip with massive power-burning buffers to fix phantom problems.
So POCV introduces a more realistic, statistical approach to variation.
Exactly. POCV replaces fixed worst-case numbers with statistical probability distributions. It acknowledges the physical reality that while some transistors on a path will undoubtedly manufacture a little slower, others on that exact same path will inevitably manufacture a little faster. Statistically, they average each other out. POCV applies Gaussian normal distribution curve to the delay of each cell. By utilizing standard deviations and root-sum square probability math, POCV allows designers to close timing with realistic margins, preventing them from over-designing the chip and wasting power to fix statistically impossible worst-case scenarios.
So you basically stop building bunkers for an apocalypse that mathematically won't happen.
Exactly.
Alongside time enclosure, we have physical verification, primarily DRC and LVS checks.
Right. DRC is design rule checking. The foundry provides an incredibly dense rulebook of geometric lithography constraints, minimum allowable spacing between wires, minimum wire widths, exact enclosure rules for VS.
You got to follow the rules.
Right. The DRC tool meticulously scans the entire multi-layered geometric layout to ensure absolutely no rule is violated, mathematically guaranteeing the chip can actually be printed by the optical lithography machines without shorting or failing. And then LVS is layout versus schematic.
What does that do?
The tool analyzes the final physical polygons of the layout, deduces what transistors and wires they form, builds a completely new netlist from scratch based on that physical geometry, and compares it against your original synthesized netlist to ensure no connections were broken or inadvertently shorted during the chaotic routing phase.
Finally, we have parasitic extraction, which determines the RC values, the resistance and capacitance, introduced by the physical wires themselves. How does the tool calculate this on a microscopic scale?
Early in the flow during synthesis, we didn't know the physical length or routing path of the wires, so wire delay was a gross estimate. Now the extraction tool uses a 3D field solver. It analyzes the exact physical dimensions of every routed metal trace, the dielectric material surrounding it, and its proximity to neighboring wires on all sides to calculate the exact parasitic capacitance and resistance of every millimeter of metal.
And then?
We feed those massive RC values back into the STA tool one last time to ensure the real physical wires haven't broken the delicate timing we achieved.
Once that final parasitically annotated STA run is clean, and once the DRC and LVS checks return 0 errors, we cross the finish line. We reach tape out.
Tape out is simultaneously the most stressful and exhilarating moment in a physical designer's career. All the design databases are locked and frozen. The multi-layered physical layout is exported into an archaic, yet universal, standardized binary file format called GDSII.
Graphic Data System 2. The term tape out is a historical relic from the early days of the industry, isn't it?
It is. In the 1970s and 80s, the final GDSII file was so large that it had to be written onto a physical magnetic reel-to-reel tape. The lead engineer would physically carry that heavy tape out of the building and mail it to the fabrication plant.
Oh, wow. Physically mail it.
Yeah. Today, the massive file is transferred securely over encrypted cloud networks, but the momentous milestone retains the name tape out. That GDSII file goes to a foundry where it drives the electron beam machines that manufacture the ultra-expensive quartz photomasks, which will eventually print your Metropolis onto a silicon wafer.
The journey from behavioral specification to physical silicon is complete. We have engineered a custom ASIC.
We did it.
However, As we discussed with electromigration and variation, the physical laws governing this space are getting brutally unforgiving. The metropolis is becoming too dense. Where does the semiconductor industry go from here?
The sources outline a fascinating, almost science fiction horizon. We are currently entering what the industry refers to as the angstrom era. We are hitting the absolute physical limits of FinFET transistors.
What happens at those limits?
As we shrink the transistor to the 3 nanometer node and below, the channel distance between the source and drain becomes so incredibly short that the gate structure can no longer exert enough electrostatic control over the flow of electrons. This leads to massive subthreshold leakage current. The transistor cannot fully turn off. To continue scaling, the entire industry is shifting away from FinFETs to GAEFETs, gate-all-around field effect transistors.
A FinFET wraps the gate around three sides of a silicon fin. So a gate-all-around architecture completely surrounds the channel on all four sides.
Precisely. They stack microscopic horizontal nanosheets of silicon and wrap the gate material completely around every single sheet. It restores absolute electrostatic control, halting the leakage current. However, novel transistor architecture alone isn't sufficient to maintain Moore's law. The industry is being forced to adopt STCO system technology co-optimization. We are no longer merely shrinking transistors in 2D space. We are fundamentally reorganizing the 3D architecture of how the integrated circuit is constructed.
And the most dramatic manifestation of this shift mentioned in the literature is BSPDN backside power delivery networks. This is a wild concept.
It is. Recall our extensive discussion on floor planning, where we laid down the massive power grid on the topmost metal layers and how that grid creates severe routing congestion for the signal wires beneath it. With backside power delivery, the foundries are physically decoupling the power grid from the signal routing entirely. After the transistors are built on the front of the wafer, they flip the wafer over, physically grind and polish down the backside of the silicon substrate until it is microscopically thin, and route the entire power delivery network exclusively on the bottom of the chip.
You completely separate the data highways from the electrical grid. The power pushes straight up into the bottom of the transistors using through silicon vias, completely avoiding the signal routing layers above.
It initiates a complete architectural revolution. It frees up massive amounts of routing resources on the front side of the chip, alleviating the congestion nightmares. Furthermore, because you are routing power on the backside without competing for space with signal wires, you can utilize much thicker, wider, lower resistance metal lines, profoundly mitigating the dynamic IR drop problems we battled earlier.
It isn't just the physical architecture and manufacturing that is changing, though. The way human engineers interact with the EA tools to design these structures is evolving at a breakneck pace thanks to artificial intelligence.
Oh yeah, AI is actively transforming the physical design flow. We already discussed the use of predictive machine learning to foresee routing congestion in thermal hotspots. But the frontier is now reinforcement learning platforms, such as Synopsys DSO.ai.
DSO standing for Design Space Optimization.
Right. DSO.ai treats the incredibly complex EDA toolchain as a constrained environment, exactly the same way an AI agent learns to master chess or Go. The agent autonomously explores millions of permutations of tool hyperparameters, tweaking placement density targets, adjusting cell sizing weights, modifying clock tree topologies, relentlessly searching for the absolute optimal PPA signature.
Wow.
It can execute massive automated explorations across a server farm overnight, uncovering placement configurations and timing optimizations that a human designer would never logically deduce.
It is essentially brute forcing brilliance by exploring the entire state space of possible designs. But the sources indicate that technology is pushing even further with CFM circuit foundation models.
CFMs represent the semiconductor equivalent of large language models. But instead of being trained on billions of parameters of internet text, they are pre-trained on massive proprietary databases of unlabeled circuit designs, historical gate-level netlists, and physical layout geometries.
Incredible.
These specialized foundation models can be fine-tuned to instantly predict standard cell delays without running complex physics calculations, or even theoretically to generate functional HDO code directly from natural language text specifications.
Generative AI applied directly to hardware design. That is simultaneously an incredible leap forward and, honestly, a slightly terrifying prospect for the industry.
It definitely signals a fundamental paradigm shift in the daily role of the VLSI engineer.
Let's reflect on the monumental journey we've undertaken today. We started by examining the brutal economics of modern 5G infrastructure, realizing that the staggering $18 million upfront NRE of an ASIC is completely justified by a $6.20 unit cost and massive power efficiency at scale. We navigated the meticulous front-end architecture, writing behavioral code, and mathematically proving its perfection through formal verification. We injected scan chains and EDT compression logic to unearth physical manufacturing defects. We painstakingly planned the power grids, placed the standard cells, and orchestrated the heartbeat of the chip, utilizing the elegance of useful skew during clock tree synthesis.
It's a lot of steps.
We fought back the electron wind of electromigration with via pillars and battled dynamic IR drop with localized decoupling capacitors. We signed it all off with statistical timing analysis, passed the DRC rules, and taped out the GDSII file to the foundry. The sheer scale of human ingenuity required to conceptualize and manufacture a single ASIC is staggering. It is, without a doubt, building a microscopic, perfectly functioning metropolis.
It represents the pinnacle of collaborative engineering. Millions of hours of human intellectual effort, decades of foundational physics research, and incredibly sophisticated software algorithms, all converging onto a sliver of silicon you can balance on your fingertip.
As we conclude this deep dive, I want to leave you with a final, provocative thought. We just explored how reinforcement learning agents are autonomously exploring millions of design permutations, and how circuit foundation models are beginning to generate hardware code. As these AI tools assume control over more of the design space exploration, the tedious routing fixes, and potentially even the initial RTL code generation, will the role of the VLSI engineer inevitably shift from a designer of circuits to a manager of AI agents?
That's the big question.
You won't be manually laying out the streets of the microscopic metropolis yourself. You will be writing the constraints and the rules for the AI city planner. When the machine designs the machine, what does the next generation of custom silicon actually look like? And what physical barriers will it break next?
It is a profound existential question for the field. The laws of physics will always remain the ultimate boundary, but how we interface with them is on the verge of a total revolution.
It certainly is. Thank you for joining us on this incredible journey down to the atomic level. Keep exploring the microscopic structures powering our macroscopic lives. We'll see you next time.